Welcome back. In this part 5, I'm going to discuss exponential decay of correlations at high temperatures. And of course, the main parts of this mini course are parts 3 and 4. So this is a kind of appendix or anticlimax, but I think this is also interesting. Okay, so let's get started. So again, let me go back to general dimension D. So this is a D-dimensional hypercubic lattice, and this again denotes a set of all bonds. And here bonds are not unordered, unoriented. Okay, and we take into account periodic boundary condition. And this is collection of all these spin angle variables. This is integration, and we don't have any magnetic field. So this is our Hamiltonian. This is partition function. This is expectation value. And the main theorem is this. For beta in this range, so it means high temperature, this 2-point correlation functions satisfies this these inequalities. And actually, this inequality, this is called the Griffith's first inequality, and it's valid for any beta, okay, any positive beta. But anyway, the main thing is this, okay. And this for this beta in this range, this factor is strictly less than 1, so this means that 2-point correlation function decays exponentially if the distance grows. Okay, so in order to prove this, we developed something called random current representation. Oh, it's a simple thing, but I think it's kind of fun. And so let WW prime be a bond, and consider this thing, which appears in the Boltzmann factor. And here we have cosine, but I write cosine in terms of exponential, like this, okay? And then this is a bit complicated, but we have exponential and to the exponential and two things. So you can write this as a product of two exponentials, and you can just Taylor expand these to get this, okay? So you Taylor expand this, and you also Taylor expand this thing and we write them together. So this is double sum over n and n prime, and okay, you have this. This is usual. And then here I have two non-negative integers n and n prime. And let me call this n w w prime, and interpret this. This is just an arbitrary interpretation, but this is convenient. Interpret this as current from W to W prime. And then I write n prime like n W prime W, and interpret this as current from W prime to W. Okay. And now I have to distinguish between W prime and W prime W. And so I introduce the set of ordered bonds, B bar. This is basically the same as this, but twice bigger. Okay. Now I distinguish between this and this. Okay. So so when I write like this, then this is the set. So these are the same. Okay. Now here they denote a pair, ordered pair, so they are different. Okay. So this is B bar. And I denote by n, boldface n, the current configuration, which is simply just a collection of NWW prime current for all ordered bonds. Okay, and this takes these non-negative values. Okay, and these are shorthand notations. This means the sum of everything, and this means that the product of all factorials. And if you encounter 0 factorial, it's 1. We define like this. Okay, this is just notation, but why did I do this? Well, notation is convenient because this is our Boltzmann factor, which is written like this. And then you can do the same thing. You can do this expansion for each bond to obtain, yes, this expression. Okay, and okay, so this is just a straightforward rewriting of this thing for each bond, and you get this. Now here we have product over all ordered bonds, and then I reorganize this summation, reorganize this product as a product over sites. Okay, and then you have to sit down and think a little bit, but then you will find that it's written in this way. Now this is theta w, and what is this? Oh, this is divergence n. How do you define this? Well, this is the definition. Okay, so first of all, this looks like divergence because now I'm summing over W prime, which is neighboring to W. And so this counts the current going out from W to W prime. And this guy is current coming in from W prime to W. So this, I take it, I count this with minus sign. So this is precisely the divergence. I mean, you can interpret, if you regard this as current, and then this is precisely the divergence. And if you sit down and think carefully, you find that this is reorganized like this precisely by using this divergence. Okay, now this is just Boltzmann factor we want to integrate over all theta, but this is very simple. The only thing we have to notice this. Here m is an integer, and we do this integration, then the result is either 2 pi or 0. Okay, when m equals 0, we have 2 pi, otherwise we have 0. Okay, and we simply do this, we simply use this for all possible theta, all possible w, and then you just integrate this to find that your result is 0 whenever this is non-zero. Okay, so the result, the only non-zero contribution comes from here. So you have 2 pi to the number of sites, to the power of the number of sites, and you must sum over all current configuration, which are divergence free. Okay, this means that this is 0 for all w. Okay? That's why I have both face 0. Okay, so I restrict some to the current configurations which are divergent free, and sum over this factor, this combinatorial factor. Okay, so this is an interesting stochastic geometric representation in terms of random currents. So this is an example of random current, which is divergence free. Okay, so divergence free means that at each site, the number of incoming bond and outgoing bond arrow are the same. So here, 1 in, 1 out. Here, I think 2 in, 2 out. Everywhere, this is 2 in, 2 out. Here, I think 1, 2, 3 is coming in, 1, 2, 3 is coming out, 3 in, 3 out. Anyway, it's totally divergence free. Okay, so this is a random current representation for Z. Now, I look at the corresponding random current representation for correlation, especially unnormalized correlation, this thing. And then this is expressed like this. It's very close to what we had for partition function, but here we have this. Okay, and so I do the same thing for this part to get this expression. This is exactly the same as the partition function, but now I have extra thing. And now I want to integrate over theta, and then I think you see what's going on here. For most of theta w, it's the same. This must be 0. But when w equals u, then here you have I theta u. So this means that in order to cancel this, this divergence must be 1. And for w equal v, then you have this thing. So in order to cancel this, you have to have this divergence. You see that this divergence must be -1. Okay, this is, I think this is nice. And so the result of integration is again the same thing. And now the sum is not over divergence free n, but this is the summation over current configuration with a current from u to v. More precisely, this is n such that divergence at u is 1, divergence at v is -1, and otherwise it's divergence free. Okay, so you sum over all such configuration the same factor. Okay, so this is the exact stochastic geometric representation. And here you see that this is simply the sum of positive factors. So this summation is of course non-negative, and of course z is non-negative. So this proves that this is non-negative for any beta. Okay, right. And what else? Okay, so this is one example. This is an example of current configuration where we have a current from u to v. So at u, I think we have 3 arrows going out and 2 arrows coming in. So yeah, it has divergence exactly 1. And at v, you have 2 coming in arrows and 1 going out current. So the divergence is -1. Otherwise, it's again divergence is 0 everywhere. Okay. And Okay, so these were these were basic stochastic geometric representations for the partition function and a normalized correlation function. So from this you get random current representation for correlation function, but we have to anyway evaluate this. And there are many ways of doing this, but let me use self-avoiding walk here. So here is a basic lemma. So suppose that we are given current configuration in this set. So there is a current from U to V. And then we can prove that there exists a self-avoiding random walk that connects U and V. Okay, and with m steps. So let me be more precise. Okay, so I can prove that there exists a sequence W, and this is just a sequence of that is sites, such that the first site is U, and the final site is V, and whenever J and J prime are different, this should be J prime, when they are different, then they are different. Okay, so this means that you never visit the same site. So this means it's self-avoiding. And also, it is satisfied that this whenever these name when they are the index are neighboring, and then this belongs to this set of ordered bonds. And moreover, this is very important, for any of neighboring these two sites, this current must be at least one. Okay, there must be some current. So I'm saying that I'm using these current to form a random walk that start from U, a self-avoiding random walk with m steps, which start from U and ends at V. Okay, so this is in a sense a graph theoretic lemma, very elementary one, and you can prove this in various manners. But let me just show you a constructive proof based on some graphic notations. So, okay, so of course I can explain this mathematically, but I think this graphic explanation will suffice, and you can easily convert this into more mathematically looking proof. Okay, so now here you have a random current representation. Random current. Here is a current. No. Here is a current configuration where there is a which satisfies this condition that you have divergence 1 here and divergence -1 here, and divergence 3 otherwise. Okay. Now we look at this point U. Okay, now we know that divergence here is 1. And it means that there must be at least one outgoing arrow. Otherwise, you can never have divergence 1. Okay, in this case, there are plenty of, but always divergence 1 ensures that there is at least one outgoing arrow. Okay, so you pick one of them. Okay, if there is a unique one, that's okay, but there are a bunch of them. So anyway, suppose that you pick this one. Okay, and now you are here. And consider all the arrows, all the blue ones. So I already used this one, so I forget about this thing. And then if you consider the rest of arrows, then you see that divergence at this site is again 1. Why? Because it was divergence free to begin with, but then I deleted this red bond, incoming bond. This means that there must be extra one outgoing bond, one outgoing current. So this has divergence 1. So again, by the same logic, you can always choose at least one outgoing arrow, outgoing current. So suppose that you want to go here, but suppose that you picked up this. Okay, and here again, now if you forget this red thing, and then there is one incoming and two outgoing. Again, you have divergence 1, and you can always choose one outgoing arrow. You chose this. And here, again, if you forget this, now it's clear that it's divergence 1, and there's only one choice. You must pick this one. Okay, here, divergence 1. Here, again, we came back here. We came back here. And after, now we don't consider all these red things. So we only consider these 3 blue arrows. And again, of course, divergence is 1. And you choose any of one outgoing arrow. So suppose that you chose this. Okay. and you choose this. And here, of course, you want to go this, but for some reason you want this. And again, the choice is unique. You come back here. The choice is unique. You have to choose this. You have to choose this. You have to choose this. And you came here. Okay. And it was not an accident that we reached V. Okay. Because this is a proof. You never stop except at site V, because of this reason that whenever you visit a new place, your divergence is 1, except except when you are at V. Okay, so whenever you are at site other than V, your divergence is always 1, and you can always travel. You can always keep on going until you come to V. So there is no danger that you go somewhere else and never come back to V. Okay, you always reach V. This has been proved. Okay, now you just forget about all these blue things, and you get this red path, red walk from U to V. But this is not yet self-avoiding. These are it intersects with itself. But this is not a big problem because you always can look at these self-intersections and delete them. Okay, so you deleted this, and you also delete this, and then you get a self-avoiding walk from U to V. In this case, it's 1, 2, 3, 4, 5, 6. Okay, 6 steps. And I think you are convinced that you can always do this in any case. Okay, so I think you agree that this lemma has been proved. Then we try to get an upper bound on the correlation function. Okay, so we take arbitrary current configuration from here. So there's a current from U to V, and then you can construct a self-avoiding walk from U to V. Okay, and then after construction, we define new current configuration called n prime by this. Okay, now I think you can guess what we do. So whenever there is a random walk, and then you subtract 1 from n, and otherwise it's the same. Okay, then rather clearly this new thing is divergence free. Okay, I think this is obvious, but let me show this. So this is the same configuration as before, and it's almost divergence free, but it has divergence 1 here and divergence -1 here. And this is our self-avoiding walk. Okay, it comes from here and it ends here. And so you just take away these red bonds and you're left with n prime. And now, of course, this side has divergence 0. I think you have 1, 2, 3 outgoing arrow, 1, 2, 3 incoming arrow, and V is really, this is really divergence free. Nothing is coming in, nothing is coming out. Okay, so I think this was clear. So we have shown this, and of course by definition we have this, and also this is just obvious because this may small. So I mean this follows from the trivial inequality that this is this for any n greater than 1 equal to 1. Okay, so we have this. Okay, now we can upper bound this unnormalized correlation function. Okay, so in order to upper bound this, I first sum over all self-avoiding walks from U to V. Okay, and then I then sum over all n by the condition that W is obtained from n. Okay, and since several different W's are obtained from a single n, this is a overcounting. This is an overcounting, but still, since you find, okay, from the fact that you always find a random walk from n in this thing, this is an overcounting, but this is a reverse upper bound. Okay, and then what we want to do is replace this summation by summation over divergence free n prime, which is related to n by this thing. Okay, and this again is a tremendous overcounting because now I'm not restricting this n prime to anything. So this n prime may have overlap with W. And in that sense, in that case, I doesn't make sense in this kind of construction. But anyway, this is a valid upper bound. Okay. Probably I'm too sloppy in my explanation, but if you sit down and think about this, it's clear. Okay. So I have this rigorous upper bound, but why did I do this? Because if you recall equation 4 in page 3, this is nothing but the stochastic geometric representation of the partition function itself. So we have partition function here. So you can just divide both hand side by partition function, then you get upper bound of this thing in terms of random walk. Okay. So this is the upper bound we obtained. Very easy. Now, now the proof is almost at the end. So we want to evaluate this summation over all possible random walks. And then this is upper bounded like this. Okay, so first of all, I note that the number of steps of random walk connecting U and V, when this is valid, must be at least U minus the distance between them. Okay, could be larger than that. This is at least you have to be this. And here, NM is the number of m-step self-avoiding walks connecting U and V. Okay, and we have this factor here. Okay, so this is just an upper bound, and then we need to evaluate this entropic factor, the number of self-avoiding walks. And of course, this is not an easy problem, but to get an upper bound is quite easy, and I want to be easy. So in the first step, you start from U, and then you can go to basically you can go to any direction. So there are 4 choices in this case. In D dimension, you have 2D choices. And in the next step, or in all the steps until m minus 1 step, you came from here. So your choice for the next step is at most 3. Okay, or at most 2D minus 1. Of course, I mean, this is just at most. Some of the sites are maybe already used, and in that case, your choice, you have fewer choices. But anyway, this is at most you have this choice. And in the final step, you have to come to V. Okay, so you can do this only when you are very close to V, 1 step from V, and in this case, your choice is only unique. Okay. And usually you have 0 choices. But anyway, your choice is at most 1. Okay, so if you multiply all of this, you find this upper bound, and I want to be easy, I just upper bound this by this. Okay, and then I just plug this in here to find that this 2-point correlation function is upper bounded like this, and this is just a simple geometric series, so you can sum this exactly to get this. Okay, so this is why we get this weird factor. Okay, and of course, this is convergent. Of course, this makes sense only when this is strictly less than 1. Okay, so this means that we are in high temperature, and this is strictly less than 1, so this shows that this 2-point correlation function decays exponentially. Okay, so that's the end of the proof, and this is the end of this mini course on the absence of ferromagnetic order in the 2-dimensional XY model. I hope you enjoyed, and thank you very much for watching.